So we worked around instantaneous velocity and acceleration when we studied motion in one dimension. And in fact, I would encourage you to revisit that chapter before you go on to this chapter on motion in 2 and 3 dimension. Now we'll be revisiting the same thing in this chapter, that is motion in 2 and 3 dimension. The only difference is that now we'll be dealing in vector quantity rather than numbers, what we were dealing in when we were studying motion in 1 dimension. So we know that average velocity is nothing but displacement upon time, and this can be written as the difference of final position, let's say it's x2 minus the initial position x1 on the time it takes to move from position x1 to x2. Now this is the way we did in motion in 1 dimension. Now what we do in motion in 2 dimension and 3 dimension is that we say that V average is equal to displacement, which is represented as R2, let's say it is, minus the position vector R1, which is the initial position vector, divided by the time taken to move from position vector R1 to R2. Now this can be written as delta R upon delta T, where delta R is the difference of R2 and R1, and then this can be written as delta xi plus delta yj plus delta zk divided by delta t. And if we put this in a graphical form, and let us say this is the position of the point as it moves, let us say this is the curve which we get on an xy plane as the point moves, and let's say its position vector at t1 is, let us say, this, and at time t2 it becomes, let's say, this. So let's show it as a vector. So this is your initial position vector, let's call this r1, and this is your final position vector at time t2, and let's call this r2. So this is time t1, this is time t2. So before we move ahead, let me make a quick tangent at t1 on the curve, and we'll get to understand why I made the tangent later on. So here is a tangent at point t1 on the curve. So you see, we can say that the delta r vector is nothing but this, and we say, let's call this delta r, and that's how we get our average velocity, delta r upon delta t, and delta t is t2 minus t1. Now this is the average velocity, and this average velocity is also in the direction of vector delta r. Now if we are asked to find the instantaneous velocity at, let's say, time t1, or the velocity which is occurring at this point, what is the velocity? Not the average velocity, but the velocity at this point of time. So how we'll go about finding the velocity at this point of time is, we will reduce delta t, we'll keep reducing delta t till it becomes very, very small, or it kind of tends to a value of 0. And when this happens, what you'll find is that the vector r moves from r2 towards r1, because we're reducing t2 minus t1. So your vector would probably start looking like this. Difference between t2 and t1, your position vector will keep moving in this direction till the position vector almost reaches t1. And you would also see that the vector delta r, which is right now r2 minus r1, will also keep reducing in length. You see, you have this as delta r, then you have this as a delta r which is smaller than the earlier one, and then again you have a delta r which is smaller, still smaller, till it reaches this point where delta r becomes really small. And if you keep reducing delta t towards 0, you will see delta r would also tend towards 0, and what will happen is that the delta r, when delta t tends to 0, would become a line which is parallel to this tangent we have drawn, and this would then be the instantaneous velocity at time t1. Point number 1 would be, as delta t tends to 0, 1, your position vector would move towards r1. The second point is that the delta r will keep reducing, and direction of delta r being a vector, will eventually converge with the direction of the tangent at time t1 when delta r is almost 0, not 0. And when this happens, delta r upon delta t value would be nothing but the instantaneous velocity at that point of time. So we can write that when delta t tends towards 0, the average velocity reaches its limiting value, and that is called the instantaneous velocity, and in mathematical terms it's shown as dr upon dt. So if we write v is equal to dr upon dt, then this would be equal to d upon dt of r expressed vector in ijk form, which then can be written as d upon dt of xi plus d upon dt of yj plus d upon dt of zk, which then is nothing but velocity in x direction plus velocity in y direction plus velocity in z direction. So instantaneous velocity can be shown in this manner. So let us take the previous example, what we solved in the earlier lesson, where we had the spider whose position was given by vector r equal to minus t square plus 2t plus 6 times I plus minus 2t square minus 4t plus 6 times j. And this is nothing but you have the x component expressed as a function of time over here, and the y component of the position vector again expressed as a function of time. So you see x and y are varying with time. Now if this is the situation, then we can say that instantaneous velocity of the spider at any time v is equal to dr upon dt, which is equal to minus 2t plus 2 times I plus minus 4t minus 4 times j. And so if you're asked to find the velocity, or rather the instantaneous velocity of the spider at time t equal to 2 seconds, what you will do is you'll substitute the value of t in this equation to find velocity is equal to minus 2 into 2 plus 2 times I plus minus 4 into 2 minus 4 times j. And you'll find that velocity equals therefore minus 2I minus 12j. Now this essentially means that the instantaneous velocity of the spider at time t equal to 2 seconds is minus 2 meters per second in x direction and minus 12 meters per second in y direction. So let's see how we interpret this on a graph. So let's say the position of the spider on the graph looks something like this, and let us say its position at time t equal to 2 seconds is over here. So this is the position vector of the spider at time t equal to 2 seconds. This is the position vector, and we have found that the velocity of the spider at t equal to 2 seconds, and let's label it as t equal to 2 seconds, is minus 2 in x direction. So in the x direction your velocity would be this, and in the y direction it would be this. So you have minus 2 meters per second over here. This vector is minus 2 meters per second, and this vector is minus 12 meters per second. So you would see that the resultant velocity of this would be something like this. See, if you use the parallelogram method, it would be something like this. And you would see that this is almost like a tangent to this point. If you extend this line in the reverse direction, you'll find that it's a tangent at this point. So you see, we found the instantaneous velocity in a mathematical way, and when we plotted it on the graph, we saw that it's just what we've just discussed, that it's tangent at that time, and that's instantaneous velocity. Now, to take the topic a little further, we might want to discuss what is instantaneous acceleration. So we know again that average acceleration is given as A average is equal to final velocity minus initial velocity upon the time it takes to change this velocity. And it's often written as delta V upon delta T. And as delta T tends towards 0, your A average moves towards something called a limiting value, and that's called the acceleration at that point of time. And that is written as A is equal to dv upon dt. So you can write A as equal to d upon dt and V expressed in vector form, and this equals d upon dt of Vx I plus d upon dt of Vy component in j direction plus d upon dt of Vz, or the scalar component in z direction, into k, and which you would see that dvx upon dt is nothing but the component of acceleration in x direction. It can be written as this, plus likewise component of acceleration in y direction and component of acceleration in z direction. So this is your instantaneous acceleration.